Welcome to this lecture on microfluidic stochastic resonance, a counterintuitive phenomenon where noise amplifies weak biochemical signals. In this system, isolated droplets flow through microfluidic channels and, remarkably, adding controlled noise enhances rather than degrades signal detection. Let us begin with the conventional understanding. In ordinary sensing systems, random fluctuations degrade signal quality. Here we see a weak periodic signal, the blue curve, that is corrupted by random noise shown as red dots. The signal becomes buried and nearly undetectable. In classical macroscopic sensors, the signal-to-noise ratio degrades linearly with increasing noise amplitude. More noise always means worse detection. The signal-to-noise ratio is simply the signal amplitude divided by the noise standard deviation. Larger noise in the denominator reduces this ratio. At the microscale, the challenge becomes even more severe due to fundamental molecular fluctuations. In small droplets of femtoliter to picoliter volume, each compartment contains only tens to hundreds of molecules. This small number leads to enormous relative fluctuations. The relative fluctuation scales as 1 over the square root of the number of molecules, n. For 100 molecules, fluctuations are 10%, which is huge. So with 100 molecules, the shot noise is about 10% of the signal. This stochastic noise typically overwhelms subtle concentration changes we wish to detect. This leads us to a profound question. Can we somehow turn this unavoidable noise into an advantage rather than a liability? The answer is yes, through a phenomenon called stochastic resonance. Let us understand the core concept. Imagine a particle, the red circle, trapped in a double well potential. A weak periodic signal, shown by the yellow arrow, tries to push it over the barrier but fails because the signal is too small. Now add noise, represented by the green fluctuations. The noise provides random kicks that can help the particle jump over the barrier when the weak signal is also pushing in the right direction. When the frequency of the noise matches the characteristic timescale of the system, synchronization occurs. The particle hops between wells in rhythm with the weak signal. The output becomes proportional to the signal multiplied by the noise correlation function. This is the essence of stochastic resonance. Noise and signal cooperate. Now let us see how this abstract concept is implemented in a microfluidic chip with flowing droplets. Droplets carrying weak biochemical signals flow through a microfluidic channel. Each droplet is an isolated reaction chamber containing the molecules of interest. Researchers deliberately introduce controlled noise through temporal fluctuations. This can be temperature oscillations, reagent concentration pulses, or electric field modulations applied to the flowing droplets. The three main noise sources are temperature fluctuations, periodic injection of reagents, or oscillating electric fields across the channel. The critical step is achieving the resonance condition through frequency matching. The angular frequency of the applied noise must approximately equal 1 over the characteristic reaction time tau. This is the resonance condition. When resonance is achieved, the weak input signal on the left is amplified into a much larger, more coherent output signal on the right. The noise has constructively enhanced the signal. For biochemical reactions in droplets, characteristic times range from milliseconds to seconds, so noise frequencies of 1 to 1000 Hz are optimal. This gives noise modulation frequencies from 1 Hz to 1 kHz, which are easily achievable with temperature controllers or valve actuators. A natural question arises. Why use droplets instead of bulk solution? The answer lies in their unique properties as isolated oscillators. Each droplet acts as an independent nonlinear oscillator. There is no crosstalk between droplets because they are physically isolated by the immiscible carrier oil. This isolation is crucial. In bulk solution, molecules diffuse and mix, destroying the coherence of the resonance effect. Droplets prevent this. Because droplets flow continuously through the chip, we obtain thousands to hundreds of thousands of independent measurements per second, creating a clean statistical ensemble. Typical microfluidic systems process 1,000 to 100,000 droplets per second, providing enormous statistical power for detecting weak signals. Let us now examine the biochemical reaction itself, which must behave as a two-state system for resonance to occur. The biochemical system oscillates between an inactive state, shown in blue, and an active state, shown in red. Forward and backward rate constants K plus and K minus govern the transitions. The rate equation describes how the probability of being in the active state changes. This is a simple, first-order kinetic scheme. Typical examples include enzyme activation, protein conformational switches, or ligand-receptor binding events that exhibit bistable kinetics. The key to stochastic resonance is threshold crossing. The weak signal alone cannot activate the system, but noise enables crossing. The red line represents the activation threshold. The weak signal alone, blue arrow, cannot reach it, but signal plus noise, yellow arrow, crosses the threshold. The noise provides random kicks that occasionally push the system over the activation barrier when the weak signal is also contributing. The probability of crossing scales exponentially with the energy barrier delta E divided by an effective temperature that includes the noise contribution. Now comes the resonance magic, synchronization between the noise fluctuations and the weak signal. The weak signal and noise, both oscillating at matched frequencies, combine constructively. The output shows a much larger amplitude than the input signal alone. Phase locking occurs. The droplet hops between reactive and non-reactive states in step with the weak input signal, synchronized by the noise. The average output scales as the signal amplitude times a quality factor Q that depends on how well the noise frequency matches the system dynamics. Detection is performed optically by tracking fluorescence bursts or colorimetric changes in individual droplets. A laser beam illuminates the droplets as they pass through the detection zone. Active droplets emit fluorescence bursts, shown by the red arrow, which are captured by a photodetector. The active biochemical state emits fluorescent light, while the inactive state does not. This provides a binary readout of the reaction state. The fluorescence intensity is proportional to the concentration of molecules in the active state, allowing quantitative measurement. Modern high-speed cameras can capture 10,000 frames per second, enabling single droplet resolution even at high throughput rates. Let us quantify the amplification. Experiments have measured the gain factor comparing output to input signal strength. The amplification factor is the ratio of output amplitude to input amplitude. Typical values are 10-fold or greater under optimal resonance conditions. Experimentally measured gains range from 10 to 30, meaning signals that would be undetectable become clearly visible. This is remarkable. Biochemical signals that would be completely lost in molecular shot noise become detectable and measurable. Let us perform a back-of-envelope calculation to estimate the signal-to-noise ratio improvement. Consider an input signal amplitude of 0.1 concentration units with 100 molecules giving shot noise of 10. The input signal-to-noise ratio is 0.01, essentially undetectable. With a gain of 10 from stochastic resonance, the output signal-to-noise ratio becomes 0.1, which is marginally detectable above noise. The improvement factor is tenfold. This calculation shows how stochastic resonance rescues weak signals from the noise floor. The signal transitions from being undetectable to measurable, opening new possibilities for ultrasensitive biochemical detection. A deeper question: why does adding noise improve detection? The answer lies in nonlinear cooperativity. The system has a nonlinear threshold response, shown by this curve. Below threshold, output is minimal. Above threshold, output saturates. The threshold region is where resonance acts. Noise allows the system to explore the steep nonlinear regime around the threshold, where small input changes produce large output changes. The derivative of response R with respect to signal S is very large at threshold, meaning high gain. Noise keeps the system dancing around this high gain region. Crucially, linear systems cannot exhibit stochastic resonance. The effect requires nonlinearity, such as threshold activation or bistable switching. This is not just theory. Multiple experimental groups have now verified microfluidic stochastic resonance in biochemical systems. This bar graph represents published experimental data showing increasing signal detection as noise amplitude is tuned to the optimal resonance value. Verified systems include enzyme kinetics in droplets, single-cell gene expression reporters, and protein folding dynamics. Measured amplification factors range from 8-fold to 25-fold, consistent with theoretical predictions from stochastic resonance theory. Let us compare this to classical electronic signal processing techniques like lock-in amplification. Lock-in amplifiers in electronics use the same underlying physics, synchronous detection with a reference signal. Microfluidic resonance is the chemical analog. We can think of stochastic resonance as a chemical lock-in amplifier, where the reference is provided by the controlled noise modulation. Both techniques extract weak periodic signals from background noise through frequency-selective amplification. What are the practical applications? Microfluidic stochastic resonance enables ultrasensitive lab-on-chip diagnostics. Droplets containing patient samples flow through a diagnostic chip. The stochastic resonance enhances weak biochemical signals, allowing for earlier disease detection and monitoring. Potential applications include early disease detection, biomarker screening, and point-of-care diagnostics for a wide range of diseases. In conclusion, microfluidic stochastic resonance offers a novel approach to signal amplification by harnessing inherent noise. By embracing the inherent noise in microfluidic systems, we can unlock new capabilities for ultrasensitive biochemical detection and analysis. Future research directions include integrating stochastic resonance with machine learning and nanotechnology to further enhance its potential. The future of biochemical detection looks promising, with stochastic resonance poised to play a key role in revolutionizing how we detect and analyze biomolecules.